Hi everybody, welcome back to Multirate Signal Processing, today about low delay filter banks. So last time we saw that an MDCT type filter bank leads to an algorithmic delay of z to the minus 1 in the lower sampling rate, hence a delay of one block over the analysis and also the synthesis filter bank. Remember, the z to the minus 1 came from making the inverse delay matrix d of z causal. In addition to this one block, we usually also need to take into account the so-called blocking delay, which results from taking into account the assembling of our incoming samples into blocks of length n. Right, so first we have to wait for n-1 samples to fill up the first block, and then we can continue to process. So we first have to wait for these n-1 incoming samples on the analysis side, and then at the arrival of the nth sample, the block is full and we can send it immediately to further processing. Hence the blocking delay is capital N-1 samples. Observe that we have no blocking delay on the synthesis side. This means the total delay is both the blocking delay plus the delay resulting from our matrices. In the case of our MDCT type filter bank, the total delay, or so-called system delay, is our blocking delay of n-1 samples plus one block delay from the polyphase matrices. So here's the total, which we call ND, the system delay, which is capital N-1 plus n is 2n-1. We also have the length of our filter, which is capital N, L equals 2n, which results in the system delay to be the length of the filters minus 1. So there's this direct connection between filter length and delay. And this direct connection holds in general for paraunitary filter banks. So any paraunitary filter bank like the MDCT, which we saw last time, has this property. So when we make those filters longer, also the delay increases. Observe that mathematically it only makes sense to define a delay over the entire analysis and synthesis filter bank, because here we have the exact same signal as the input signal, just delayed. After only the analysis, we only have subband signals which look quite differently and have a different sampling rate. Hence, here we cannot really define a delay, right? It's two totally different signals. For paraunitary filter banks, the only possibility to reduce the system delay is to reduce the filter length. So if you say the delay is too long, then all we can do is make the filter shorter. But this then degrades the filter characteristics. For instance, it would lead to reduced stop attenuation. So that's not good either. Often in applications like real-time audio communications, it is desirable to have a lower end-to-end delay, but also good filters with high stop attenuation, such that we still obtain good coding or compression performance. So we want to have good compression performance, for instance in our teleconferencing scenario, but we also want to have short delay such that we have easy communications without pauses. So there the solution are the so-called low delay filter banks. With them it is possible to reduce the system delay without reducing the filter length L. So that's basically the solution here. We keep the filter length and reduce the delay. So it's actually pretty good. So how does this work? First, how do we get longer filters than the MDCT type filter banks in the first place, right? So far we didn't even look at this possibility. For MDCT type filter banks, we only had filters of length L equals 2n. So the filters had the length of 2 blocks. So how do we make them longer? To see the solution, we first need to take a look at the polyphase matrix again, this time for filters of arbitrary length, more than 2n. So again, we can compute our folding matrix of it using our formula as before. Here we have our folding matrix with the delay matrix, and this results from taking the polyphase matrix H of our analysis filter bank, this time for longer filters. So we can just make some filter with longer filter length, put it into this matrix H, and then multiply it with the inverse DCT4 matrix. And out comes this folding matrix, which has this diamond shape and now longer filters. So as for the MDCT type filter banks, just now our analysis polyphase matrix H of Z can contain baseband impulse responses HA for the analysis with arbitrary length L, and L can be much larger than 2n here. So first we start with maybe some generic HA or some fantasy numbers which we plug in there just to see the shape of our folding matrix or filter matrix. The result from the analysis folding matrix is the same as for the MDCT type filter banks, but with higher degree polynomials in it as expected. So again we get this folding or filter matrix Fa of Z, which has this diamond shape, but now we see it has polynomials of higher order. So here this is the more general formulation. Remember, for the MDCT we had just had two coefficients, one for Z to the 0 and one for Z to the -1, and we also saw the sign change, and we saw that it corresponds to the downsampled version by a factor of 2n of the prototype. So this is what we see here again. We have a prototype downsampled by a factor of 2n. We have this sign change, every other coefficient incorporated here with a Z. And here you can see the phase, which corresponds to the entry here in the matrix. So here you can see the definition. Here the Z-transform of the downsampled sequence of the prototype downsampled by 2n with phase lowercase n. So here you can see it just the usual. We take our prototype HA downsampled by this factor of 2n with phase n and Z-transform it, and then we get those polyphase entries into this folding or filter matrix. So basically we are lucky. It gives us this simple representation for arbitrary length filters in this way. So these are the Z-transforms of the downsampled by 2n versions of our baseband prototype HA for the analysis at phases n, as I just said. The minus sign and minus Z to the second power results from our cosine modulation function changing its sign every second block, as we saw last time. Yeah, so you can also read more of it from our early papers here called New Framework for Perfect Reconstruction Filter Banks in the IEEE Transactions on Signal Processing from 1996. Observe that this Fa corresponds to Fa times d of Z. So if there's just Fa without a Z, then it's just the coefficients, and Fa with the argument Z means we have this multiplication Fa times the delay matrix of Z. So both mean the same, it's just that this Fa of Z is a shorter notation. Observe that the order of the polyphase polynomials determines the resulting filter length of our filter bank. The polyphase matrix of equation 1 processes the signal at the lower block sampling rate. Hence, an additional degree in its polyphase polynomials increase the resulting filter length by one block. So when we look at equation 1 here, we can see we have polynomials in it, and since this processes the block one after the other, when we have an additional degree here, then it means we accommodate one more block of the impulse response in it. And that means we have a block of length capital N samples, more length in the impulse response. So here we can observe two effects. One is that the shape of our analysis folding matrix has again this diamond shape that we already know. Second, the polynomials in it now have a higher order depending on the length of our filters. Right. So for the MDCT type with L equals 2n, we still get an easy solution here. But what about longer filters? Our goal is to obtain a perfect reconstruction and also to obtain finite impulse response filters for our synthesis to make it easier to handle. So the approach now is to use our previous matrix decomposition with a Fa times D times the transform matrix, writing our polyphase matrices as a product of simpler matrices, and simply extend this product with additional matrices. Right? Basically apply the same trick again, such that we keep the diamond shape of our resulting folding matrix intact, because this was the result of our cosine modulation, which we would like to keep intact, that we increase the polynomial order and hence the resulting filter length. So these conditions. And also such that we get easy FIR filter inverses and such that we can control the resulting system delay. Right? And this way we have longer filter and we can also determine the system delay. The trick now is to invent additional matrices which fulfill these requirements. These additional matrices can be split into separate types. The first type is the so-called zero delay matrix, which we can see here. So it's actually quite simple. It consists of ones on the anti-diagonal of this matrix. Then we have coefficients times z to the minus 1 on the lower half of the diagonal matrix, and the rest is zeros. Right? So simple enough. And interestingly, this matrix has an inverse which is already causal. We don't need a delay to make it causal. And that's different from our delay matrix. Remember, in the delay matrix, the z to the minus 1 turned into the z to the plus 1, which is non-causal. But if we invert this matrix, you can take a look at the result. So this is the inverse, right? The inverse of this matrix, EI. So I denotes the set of coefficients that we have here. And you can see it almost looks the same. Again, we have the ones on the anti-diagonal of this matrix. Then we have the coefficients, now with a minus sign, and still with z to the minus 1 here. Right? The multiplication with z to the minus 1, and it's on the other half of the diagonal. So it's flipped over. So basically, the lower diagonal is flipped over to the top. We change the sign here, and that's it. So here you can see, since it's still z to the minus 1, it is still a causal matrix. So we don't need any additional delay to make it causal. But we still have this z to the minus 1, which means we get a higher order polynomial if we multiply it with the rest. Right? So we increase the order to get longer polynomials, longer filters, but we don't need to increase the delay because it's already causal. So it's actually quite nice. So in SymPy we can test it. So we just choose n equals 4, and that gives us two coefficients, E0 and E1. And we start Python, for instance, in a terminal window, which I do now. So here comes my terminal. Make it a little larger. And now we start with Python. So this is the normal Python now, not IPython. So I'm using SymPy and NumPy and define my symbols here. So say copy and paste. So here I have those symbols, Z and E, which are my coefficients, which need to be determined later. So for now, they are unknowns. So Next we can construct our zero delay E matrix. Here's my E matrix. So you can see the ones, they make up the anti-diagonal, and then you can see here the lower half of the diagonal has those entries E times z to the minus 1. So here are the two coefficients, which for now are unknowns. So here just copy it, copy and paste. Let's see what's in it. Yeah, and this is exactly what we wanted. So here you can see the ones on the anti-diagonal, and then the factors E times z to the minus 1 on the lower half of the diagonal. Right. So this is the matrix that we have now, and then we can easily compute the inverse in SymPy by using to the power of minus 1, which is the inverse of the matrix. So let's try it. So here e to the power of minus 1, which gives us the inverse, and here you can see the result. So it's exactly what we just saw. So here we have the anti-diagonal, and then the diagonal is flipped to the first half, flipped over, and sign changed. Right. So here just flipped over, sign changed, and we still have z to the minus 1. So that means it's still causal. So that works. So we have a confirmation in this example that it works. So we see that this is indeed the form as above. So we can now multiply our analysis polyphase folding matrix, this equation 1, with a zero delay matrix, and get polynomials of higher order because we have elements with z to the minus 1 in it. Right? The synthesis polyphase matrix is multiplied by its inverse to still obtain perfect reconstruction. So we do that on both sides, such that we keep perfect reconstruction. Since the inverse also has polynomials of degree 1, it is still FIR. So both sides are still FIR. So this is also what we wanted. Also, since the inverse is already causal, we don't need any multiplication with z to the minus 1 to make it causal, and hence no additional delay. This means if we use this matrix, we can increase the filter length, but don't increase the delay. So that's pretty nice. In principle, we can repeat this process as often as we like and get arbitrarily high filter length, but no increase in delay. So almost sounds too good to be true, because we get something for nothing. So zero delay matrices increase the filter length by 1 block, but don't increase the system delay. We increase the filter length by 1 block because the increase of the order of the polynomials by 1, which corresponds to 1 block. There's also a second type with the same properties where we simply use the other half of the diagonal. So actually we have the choice, either use the lower half or the upper half of the diagonal for our coefficients and z to the minus 1. And the causal inverse is obtained in the same way. We just flip the diagonal and change the sign of it. So again, it's causal. So observe, contrary to diagonal matrices where we need to take the inverse of each element of the diagonal, here we obtain the inverse by flipping the diagonal half and flipping just the sign, which keeps it causal. So here's a corresponding Python SymPy example. We would like to see how this product looks like. This FA of z, which is FA, which just contains the first coefficients, originally from the MDCT, times our delay matrix, and now our zero delay matrix G of z, which contains additional coefficients to make the filter longer. So this is then our new filter matrix or folding matrix FA of z, which contains now the polyphase coefficients. Yeah, so this is our new folding matrix as FA of z with a zero delay matrix G of z. For that we write the following Python file, which we call low delay FA. So here you can see it. From SymPy we import everything, Then we define our symbols. H is now also symbols. This is going into the FA matrix, FA without the Z. And then we construct those matrices. So here you can see the FA matrix takes the H coefficients and builds the usual diamond-shaped matrix with those float numbers. Then we have the delay matrix, where we have the delays on the first half of the diagonal. And finally, our zero delay G matrix, where we have the ones on the anti-diagonal and the coefficients times z to the minus 1 on the first half of the diagonal. And then we can take a look at it and also see how the product looks like. So let's try that. So I just copy and paste this, starting from here. So I'm staying in Python, going down here, copy, paste. So now we can see the FA. This is our FA, the usual that we know from the MDCT. Then here's the D. Also the usual, here we have the delays on the first half on the diagonal and then the ones on the rest. And now the G. Here you can see the ones on the anti-diagonal and then the coefficients times z to the minus 1 on the first half of the diagonal. Right. So now we can look at the product. FA times D times G, that's FA times D times G, right? So this is what we get now. And here you can see we have higher order polynomials indeed. So now it's not only going up to the z to the minus 1, but z to the minus 2. Right, so we have indeed one additional block here, which we get as the length of our filter. So exactly what we wanted. So here you can also see it in a nice printed form. So actually it turns out that SymPy can also print out in LaTeX notation and then use it in document. So that's quite nice. Yeah. So here again is the result. Here's the D, here's the G, here's the output of the product of all three of them, and you can see it more nicely printed using the LaTeX output. Well, here's the LaTeX output. So this is a nicer notation here. So you can see it actually is suitable for documents. Yeah, and again we see here we get z to the minus 2 as the highest exponent of the polyphase matrix, of the folding matrix, and that means we have longer filters now. Yeah, so we can see that this is indeed the diamond-shaped form of equation 1. By comparing it with equation 1, we could now read out the resulting baseband prototype filter for the analysis. So this is our FA of Z, right? And then we can take it and compare it with a more general form that we found before. So when I scroll up here, we can compare it to, there we have it, this one here. So here now we have the generic form with those definitions, and then we know exactly which coefficient is which, how the HA results to the coefficients that we just computed. And this is what we could use for optimization, for instance. So going back here, right, so here you can see we have those products here, G1 times H7, G0 times H6. So here the connection between the coefficients and the resulting baseband prototype is no longer so obvious because we have more complicated expressions here. Right. So it's not that it's the direct correspondence, but more indirect. Yeah, so in this way we could read out the resulting baseband prototype filter for the analysis. Observe that equation 1 is for an even number of zero delay matrices. For odd numbers, as in this example, we would need to flip the matrix in equation 1 horizontally, flip LR, so that the exponents fit, right? Because remember, we continue on each on the left side and on the right side, and so first we have the highest coefficients on the left side, and then we have the highest coefficients on the right side, and that's why we need to flip it depending on if we have odd numbers or even numbers of zero delay matrices. But that's actually something that becomes obvious when you do the comparison. So now we don't specify HA in our design process, but we start with our coefficients of our matrices and obtain a baseband prototype HA with the desired length and delay properties. Right. So first we have some unknown coefficients, and then from those unknown coefficients we obtain then our baseband prototype, which we then can analyze and use that as part of an optimization process. So question, what is the possible drawback of these zero delay matrices? So far we saw it only has advantages because we don't pay any penalty in terms of the delay, right? So the answer, if we only increase the filter length with our zero delay matrices, we can observe that the far off attenuation increases easily, a clear improvement over the MDCT case. But the nearby attenuation to the neighboring subbands, so close to the passband, increases not as much as for orthogonal filter banks with similar length but with more delay. So here we now have a drawback, right? So the transition band and the nearby attenuation is not improved as much as using more delay. So hence it can make sense to also increase the system delay to obtain filters with higher nearby attenuation more easily. So this leads us to a matrix which is very efficient in increasing the system delay, the opposite of the zero delay matrices. So they can be used then to improve the nearby attenuation. The so-called maximum delay matrices. They basically result from exchanging or replacing z to the minus 1 by z in our zero delay matrices and a multiplication with z to the minus 1 to make them causal. So here you can see it. Here I have e of z to the minus 1, which means each z is replaced by z to the minus 1, which means we have coefficients times z to the plus 1 in our matrix. And then we need to multiply this matrix by z to the minus 1 to make it causal. And as a result, we have z to the minus 1 on the antidiagonal, and we have coefficients of z to the 0 on the first half or second half of our diagonal. So here we can do the same for the E matrix and the G matrix, depending on which half of the diagonal we have the coefficients. And I call it H1 and H2. Yeah, and also the inverse then needs a multiplication with z to the minus 2 to make it causal. So this is where we get a lot of delay. So this is the inverse of the matrix from the analysis, which we need for the synthesis for perfect reconstruction. And you can see this is the inverse of the H1 matrix times z to the minus 2. Right, so that's why we need particularly much delay to make this causal. So here H1 times H1 inverse times z to the minus 2 is z to the minus 2 for causality. Yeah, so this is then what we can use to increase our system delay. Observe that the maximum delay matrices have a polynomial of order 1, just like the zero delay matrices, and hence we increase the filter length by 1 block, but increase the delay by 2 blocks. So this is twice as much as for an orthogonal filter bank. So basically you could say that this maximum delay matrix compensates for the delay that we saved with a zero delay matrix. So if you combine one zero delay matrix with a maximum delay matrix, then we have the delay and the filter length of orthogonal filter banks. So using only maximum delay matrices would result in similar frequency responses as with only zero delay matrices. The impulse response would only appear time reversed. We get increased nearby attenuation only if we mix both types of matrices. Orthogonal filter banks can be obtained if we use the same number of maximum delay and zero delay matrices. Then we get orthogonal filter banks. So the resulting polyphase matrix for the analysis then becomes this product. So here this PA now is our polyphase matrix for the analysis, and it consists of this product. So we start with our FA matrix, this diamond-shaped folding matrix which contains real-valued entries. We multiply it with our diagonal matrix, the diagonal delay matrix, and then we have a certain number of zero delay matrices G, so P of them. And then we have another number of maximum delay matrices, Q of them. And finally, we multiply it with our DCT4 transform matrix. And here this HM, those maximum delay matrices, can be either H1 if the P for the zero delay matrices is even, or H2 if this P is odd. Again, this is the thing with the two different halves of our matrix, left half or right half. So it depends on where the highest exponent appears, on the left hand side or the right hand side. So for the synthesis polyphase matrix we get the inverse product. So we can just invert this PA of Z because each of those matrices is invertible. And for making the inverse of those maximum delay matrix causal, we need Z to the minus 2 for each of them. So we get Z to the minus 2Q plus 1. And this plus 1 comes from the zero delay matrix here. So altogether we have the inverse DCT4 transform matrix first. So we basically go from the end to the beginning and invert every matrix. Then we have to invert our maximum delay matrix. So each maximum delay matrix has a corresponding Z to the minus 2 associated with it. And here also we start from the end and go to the beginning of this product here, reverse order. And then we invert the zero delay matrices. There we don't need any additional delays. Again, doing it in the reverse order. Finally, we have the inverse of the delay matrix with a Z to the minus 1 to make it causal. And finally, the diamond-shaped FA matrix inverse. So here we have the analysis, and here we have the synthesis PS. So now we can design the impulse response length and the system delay of our filter bank. The total number of our zero delay and maximum delay matrices determines the length of our impulse response. Including the effect of the FA times D of Z matrix, a length of 2 blocks, we obtain a total filter length of 2 from the beginning, plus Q plus P, so 1 block from each of those matrices, times N, because that's the block length. So this is the resulting filter length. And just the number of maximum delay matrices, HM of Z, determines the system delay, including the effects of the FA times D of Z matrix and the blocking delay, which results in a delay of 2n minus 1. we obtain a system delay of nd equals 2n minus 1 from the beginning, and then plus 2qn. Right? This comes from the maximum delay matrices. So each zero delay and maximum delay matrix increases the impulse response length by one block of n samples. Each maximum delay matrix increases the system delay by 2 blocks, 2n samples. In this case, starting with the MDCT delay of 2n minus 1 samples. It is also possible to start with a lower delay with an MDCT by setting the leading samples of the MDCT type part to 0. So then this FA matrix would not be fully occupied. So the leading HA coefficients, H0, H1 and so on, they might be 0. And then you could move it ahead towards the origin and you would reduce the delay. Here, observe, we obtain the same analysis and synthesis baseband impulse responses if the determinants of our submatrices of our polyphase matrix are -1 as seen before. Right? So that's again convenient for design. So this is what we can still apply here. Observe that it doesn't need to be a paraunitary filter bank because the number of zero delays and maximum delay matrices can be unequal, but we can still apply this rule that we have the determinant is -1. So we don't have symmetric filters anymore as in the orthogonal case or paraunitary case, but we can still have identical analysis and synthesis baseband impulse responses by applying our constraint determinant is -1. So that's quite useful here in this case. So if we look at the zero delay matrices, we find that the determinant of the submatrices is already -1, which is very practical. So we don't need to change anything there. So this is actually part of the minus here. If you look at the maximum delay matrices, we see that the determinant of the submatrices is -z⁻², which is their resulting delay contribution and a factor of -1. So again, it works, which has the same effect of leading to the same analysis and synthesis impulse responses. So convenient again. All we need to remain to do is to make sure that the matrix FA has a determinant of -1 in their submatrices to obtain identical analysis and synthesis baseband impulse responses. This means the number of unknown coefficients for the folding matrix FA is going down from 2n to 2n minus n over 2, coming from the n over 2 submatrices having a constraint of determinant equals -1. Right. So then we have fewer freely choosable coefficients. This also makes the design easier because then we only need to optimize one side of our filter bank, the analysis, for instance, and we have a reduced number of coefficients. Instead of 2n, we have just 1.5n. So we need a numerical optimization because we now have a long cascade or product with many unknown coefficients in the FA folding matrix, the zero delay, and maximum delay matrices. We need to optimize them such that we obtain a good frequency response for the resulting impulse response. We can use equation 1 in this lecture and our product for the folding matrix FA of Z without the transform matrix T to read out the resulting baseband impulse response HA of n. Right? So this gives us then HA of n, and then we can apply optimization to this HA of n, such that we obtain coefficients which give us the best frequency response. Yeah, so we can then compute the resulting frequency response and use that as a function to optimize towards some optimum frequency response. For instance, an ideal low-pass filter as a prototype. So that's actually the typical thing you would do. So you would have it as a target an ideal low-pass filter for the prototype and then see how close you can get to it using the coefficients of this cascade. So an example application of this type of filter bank is the audio coder Enhanced Low Delay AAC, or ELD AAC in MPEG-4. Here it is used to obtain a lower encoder decoding delay, and it's used indeed in telecommunications applications. Yeah, so now a Python fast implementation example. So would you do it when you have live audio coming in and you want to have efficient processing so that you can do the processing actually in real time. So for low delay filter banks, it is useful to process the samples as they come from the sound card, right? Because we want to have low delay. Hence, we need a different implementation, an implementation which is not based on the signal already in memory. To obtain it, we interpret the z to the minus 1 as a delay by one sample, which it is, and implement it using a memory element, which stores or delays samples with one sampling interval. So instead of having a symbolic processing, we now actually implement the z to the minus 1 indeed as a delay by one sampling interval. So in this way, we don't need to transform things in the z domain, we just implement it in the time domain. So the delay matrix d of z, for instance, can be implemented as follows. So here now, not using SymPy, but using delay elements. Here you can see it, how it works. Here I define my function, def d matrix of samples. So samples is a block from, well, not directly the audio card, but indirectly. So this comes then from the FA matrix, and the FA matrix gives the D matrix N samples, a block of audio samples, which it needs to process accordingly. So here we have this block coming from the FA matrix, block of N samples. And here now it computes the output. So first we initialize it with n zeros. Then we assign the first half of the output the delayed version from the memory element. Right? So dmatrix.z now contains the first half of the coefficients of the samples of the last block. So this is a memory element, dmatrix.z, which you can see actually initialized down here below this function. dmatrix.z is an array which contains n over 2 entries starting with zeros. So the first time it's called, it's initialized with zeros. The next time it's called, it gets actually the first half of the block assigned, right? But only after it used the content to produce the output. So this is the delay function. So it assigns the output the last entry of this delay element, and then the delay element gets the current entry for the next call. Right. So in this way, each call represents, or each call is done for each sampling interval here at the block processing interval. So D is called for each new block. And this is why we have a delay by one block now. Then the lower half of this block is easy because that was just ones for the delay matrix, which means it's just passed unchanged. So here you can see it. The last half of the block is signed to the last half of the output block. So this is exactly the function then of this delay matrix D. The first half of the block is delayed by one interval, one sampling interval or one block interval, and the second half is passed unchanged. Yeah, so it's actually quite simple when you think about it. It's actually really simple. So real-time MDCT or low delay filter bank implementation producing a waterfall spectrogram, including the synthesis filter bank and playback of the reconstructed signal, can be run with this function here. So I can open this function, quit. So first I need to go to the corresponding directory here. Multirate Summer 2020. Okay, long path. So now let me first open it. Direct play MDCT. So here you can see the implementation, and you can see I define n as 512. So here we have 512 subbands and downsampling by 512. The block size from the sound card is the same. We assume the sound card gives us 2 bytes per sample, 16-bit integer, the usual. We have mono, 1 channel, and we have 32 kilohertz sampling rate. So this is now the function for the D matrix, which is exactly what I just showed you. Here we have the memory element, which is separate, which means this is a global memory element which keeps its content between calls of this function. Then we have the same thing for the inverse D matrix. Remember, the inverse D matrix had the delays on the second half of the blocks and the lower half of the diagonal, which you can see also here. So this is the second half of the blocks, which is delayed correspondingly. Here we have the F matrix. For the F matrix, I'm using the sine window here, which we saw last time. And also I'm building this F matrix just as we saw last time here. Here the inverse is just computed as lin-alg inv from F matrix. So there's just the inverse matrix. Basically I could have also taken the transpose because this, as we know, is orthogonal. Then here is the DCT4 transform. And it uses the DCT3 to implement the DCT4 because the signal processing library FFT.DCT has the type 3 built in. So I'm just taking advantage of it. Unfortunately, it does not have the type 4. So I'm using the type 3 to implement it, which I'm doing by upsampling a block and keeping zeros in between. And upsampling means I have twice the fine sampling rate, and that means I can now implement the shift of 1/2 sample by using a shift by 1 full sample at this higher sampling rate, which you can see me starting here at 1, right, instead of 0. This corresponds a shift of a 1/2 sample at the original sampling rate. So I upsample it here, then I apply the DCT type 3 to this upsampled version. And I'm then just taking the first half of the resulting spectrum because due to the aliasing that we have from the upsampling, the second half would be identical to it. So I just keep the first half. So in this way I implement this time shift of 0.5 using upsampling. Yeah, so here's now the complete MDCT. Here without zero delay matrices, just to show you the implementation example. So this is the function you call for the analysis for each new block. So here you get a new block. Here you process the first block by multiplication with the F matrix. Just use the matrix multiplication dot. Then you apply this multiplication with the D matrix by just calling the function D matrix of Y. And then you call the function DCT4, and the result is then the resulting MDCT output block for this input block. And for the audio signal, you will continually call this MDCT function for each new arriving block from the sound card. Then in the decoder, you would apply this function MDCT inverse for the reconstruction, for the synthesis. And for each block arriving from the analysis, each block Y, you would call this function to reconstruct it, to reconstruct the original audio signal. So starting with the inverse DCT4, which is the same as the DCT4 times this normalization factor in this case. Then you apply the inverse delay matrix, DCT matrix inv, and finally you multiply it with this inverse F matrix. And X then is the reconstructed signal X hat. So then you can apply it to the running audio. So here, as usual, we open the audio card. We also construct a waterfall diagrams with 500 rows and 512 columns. Remember, chunk was 512 here. So the rows are the block numbers. And then I'm constructing this waterfall spectrum using the MDCT. So here I'm reading a block from the sound card, convert the data type to floats here. Samples then is a block of float samples. Here I shift my waterfall diagram one row up. And then I apply the MDCT to the incoming sample block. So here FFT length should be 512. Yeah, it's the same as columns. So that's our full block. The full block coming from the sound card. Here we could do some processing if we wish to. Here I compute the color, the resulting color for the waterfall spectrogram, and I show the frame, which is then the spectrogram, the moving spectrogram. Here I'm also doing the reconstruction, now using the synthesis. So here I'm taking one block of our MDCT, feed it to my synthesis filter bank, the synthesis MDCT, and XREC is then the reconstructed signal, and here I cast it as integers. So basically this takes the floats coming out here and then turns it back into integers to be able to play it back in the sound card. So here I'm also doing clipping to avoid overloading the sound card, and then I turn these integers into 16-bit integers here using PAG. And finally, I write it to the sound card. Yeah, so we have both. We have this moving waterfall and we have a reconstruction, and we can listen to this reconstruction. So hopefully we won't get a feedback from the output to the microphone. So we can try this. So now let me call this function here. Python. Let me see if it works for Python 3. Yes, 1, 2, 3. And of course it's too loud. So let me go to the sound settings, input, and maybe reduce the input somewhat. 1, 2, 3. Yeah, that seems to be better. 1, 2, 3. Test. Yeah, so this works better. But you can also hear that it's choppy. So this is because I'm using the full-length audio block, which comes from the sound card, and it's actually not fast enough processing each block in time for the next one to arrive, and that's why we get this choppiness. Yeah, but we can also take a look at the spectrogram. So here you can see it. So on the left hand side we have the low frequencies, and you see indeed we get a nice resolution of our frequencies. So 512 subbands for the MDCT, and remember the MDCT has quite sharp filters, and that's why we get pretty good resolution here at the low frequencies of my speech. Right. So that shows advantage of the MDCT. Indeed, it has very sharp filters. It has much higher resolution or much higher stop attenuation than a usual DFT or short time Fourier transform with a rectangular window. So that's good. We could also try some processing here. I have some examples. Say here I just keep the subbands between k equals 10 to k equals 149. So I assign everything else to 0 here. So this is like keeping just a narrow piece of the total spectrum. Remember, the highest frequency here is 512. So this is about 1/4 of it. So highest frequency means 16 kilohertz Nyquist frequency, and 1/4 of it would be 4 kilohertz. So this should give us roughly a telephone bandwidth. So let's try. So this is now my narrowband speech. 1, 2, 3. Yeah, so if you listen carefully, you can actually hear that all those high frequencies are missing. And you can also easily see it in the spectrogram. So here in the spectrogram, you can see the high frequencies are all blue, which means there is nothing there. It's all 0. And also the lowest frequencies here, they're all 0. And what's left is just this patch in the middle. But you can still easily understand my speech. And that's because speech is not very sensitive to changes. So speech is very robust. We can do a lot of it, and you can still understand it. Yeah, so this shows you how you would implement a low delay filter bank by using z to the -1 as delay elements, delay by 1 block interval. So you just need to have fast enough processing, and then it works. Okay, so this should be it for this part of our lecture. So thank you for your attention, and see you in the next set of slides.